much, Andy. And thanks to all of the Flash Talk speakers. I guess we can start by just highlighting some of the common themes that I noticed under the pre-recorded talks. So thanks to all who left their comments under the pre-recorded talks. And basically, I think there are some common topics that pop up in several talks at the same time, such as more topics more related to infrastructure of the models or dynamical core, like the question of latitudinal, longitudinal grids versus more exotic icosahedral grids. Then there were also some questions regarding the top of the model and the implementation of the sponge layer in different models and for different planets. Regarding the high resolution simulations of convection, there's of course the great incentive to use them to retune parameterizations for global coarse resolution models, and how we can do that is a question. And then a lot of discussion was also about some issues like non-constant heat capacity or non-dilute regimes, and how modern GCMs can handle that. And then both in atmospheric and oceanic models, we have sometimes assumptions of hydrostasy or quasi-hydrostasy. And so the question then is how applicable it is to other exoplanets, or is it computationally expensive or not? And then also, of course, the ocean models in exoplanet research is a very interesting and sometimes neglected topic, and there were a lot of questions about that. These are some of the topics I picked up, but there were also questions that have been left unanswered because they were asked maybe yesterday. So I suggest we just go over, just go through the talks, and people can ask their question personally, and then the speaker can answer them. We can start by perhaps Jeremy's talk about convection. So there were a few questions from Ray Priya-Humbert and from Daniel Cole, and also from myself. If anyone is ready to ask their question, let's do this.
So how do you want to handle this? Do you want people to raise their hands or just jump in?
Yeah, so we do it as we did yesterday. Just please raise your hand virtually using the participants button. Yeah, and then we can call you and you can unmute yourself. Well, since you're talking, Ray, let's start with you.
Okay, yeah, no, I had more comments in there than actual questions, but I put in, you can just look at it yourself. I put in a couple additional references that people might find interesting with regard to the non-dilute convection regime. As far as I know, our ExoFMS and LMD are the only models that actually attempt to put in non-dilute effects. I don't know if anybody else has put that in, but one of the remarks was that in there was to emphasize the importance of enthalpy conservation. That when you're if you don't conserve enthalpy in a convective adjustment scheme, then your top of atmosphere energy balance is messed up completely. And we know how to conserve enthalpy in the dilute case, but it takes a lot of attention to detail to conserve enthalpy properly in the non-dilute case, including things like tracking the enthalpy carried by condensate and things of that sort. And in the paper with Feng Ding that Jeremy mentioned, we do conserve enthalpy exactly, but that's a convective adjustment scheme, and it's really you just can't deal with, say, subsaturation in a saturated moist convective adjustment scheme in the non-dilute case. And so we are trying to move to mass flux schemes and getting them to work in the non-dilute case. But enthalpy conservation is more than just it engages a whole bunch of new issues that are not just in the important issues about how to formulate the adiabat. There's also an issue with formulating the adiabat with regard to the effect of retained condensate. There's this very good article by Lee and Ingersoll, which derives a reversible adiabat. And after much head scratching, we realized you can turn that into a adiabat, but literally what they derive in that is an adiabat that's realistic, but you know, in some cases, if you have small particles, 10% retention, you know, could be quite. I'll cut it off for there now. There are a couple other comments I had in there, but I don't want to take up too.
Okay.
Thanks, Ray. Maybe I can just comment to answer. Yeah, that's actually what I wanted to say, and that's great that you reinforced this. That's why I didn't want to get into discussion about this mass flux scheme over this mass flux scheme, because I think there are very basic concepts that we need to address before we get to that stage.
If I might comment or ask on Ray's comment, you mentioned that you would like to move to a mass flux scheme for a non-dilute regime, but wouldn't the mass flux assumptions, like the ratio of updrafts to downdrafts, break in an extreme non-dilute regime? How would you handle that?
Well, in fact, yeah, there's even more than that. This is why it's not at all straightforward. But as you go into the non-dilute regime, your basic way of closing the mass budget changes, because as you get more and more non-dilute, the compensating downward mass flux starts to be carried mostly by precipitation. That's what we discuss in the Procroy-Sock article. And so actually, in the limit of a pure steam atmosphere, you don't actually necessarily need any downdraft region. The mass flux can be closed in a single column. But when you're in the intermediate regime, you do need some downward dry mass flux. But it introduces another unconstrained part of the mass flux scheme, because you now have two ways of closing the mass budget, either by precipitation or by a downward dry subsidence, and you need a closure that tells you, how you balance those two things. In the dilute case, since you can't balance much mass flux by the precipitation, this issue doesn't derive. There are also various issues about where, whether that mass flux is the downward mass flux is happening within the convective tower as kind of an evaporative downdraft versus in the environment. I think the key, and what we're trying to pursue, although it's going very slowly, is to see if we can get mass flux, some kind of mass flux scheme to reproduce what we see in 3D convection models. I don't think it's so much as tuning, because we're not even close to having something where it's even legitimate to say we're tuning something. We want to see if we can get anything at all resembling what the 3D convection schemes are giving. And actually, we're starting in the case without latent heat release and just with compositional buoyancy, like in the hydrogen water case, but without water condensation. It's even tricky to get the mass flux convection schemes to give you the right, terminal atmospheric composition in that case. So in fact, there are many different neutrally stable final states that you can get, especially if you just if you just require local stability, not global stability. So it's going to be a pretty long haul.
Yeah, I guess in that case, you would need to overhaul the whole assumptions of CAPE and SYN and how they interact with, well, if you take into account the molecular weight effects.
Well, yeah, so actually, in some sense, because most convection schemes have virtual temperature in them, as long as you don't linearize it, they already take that into account in CAPE. But I think it's a bigger issue is conditional instability. The LCL in many convection schemes like the Del Genio mass flux scheme, the conditional instability is based on just lifting a parcel by one grid box, by one vertical grid box, which is actually not the right way to go because that makes it resolution dependent. But the question is, what does it actually take to trigger, conditional instability? And this becomes an even a bigger issue when you have strong compositional buoyancy, like the case of hydrogen and water that Jeremy outlined.
Right, thanks. So does anyone have any more questions or comments regarding talks about convection, either to Jeremy or me or Maxence? So please raise your hand if you do. If not, we can go back to the dynamical core talks. So please raise your hand if you have questions for Nathan or Russell, or you have any general comments about dynamical cores. Okay, well, there was a lot of discussion, if I might comment, under Russell's talk about the Thor model. And I thought it was quite interesting that Thor uses the new architecture. They use GPUs instead of CPUs. And so there were a few questions related to the efficiency and also energy costs of running GCMs on GPUs. So does anyone have any question about that? I see. Okay, Ray, do you have a comment?
Yeah. This is about the dynamical core, cores and primitive equation versus non-hydrostatic.
You're breaking off, Ray.
Hydrostatic. Actually, my internet froze up. Are you hearing me?
You may want to
repeat the last sentence?
Are you hearing me okay?
You may want to cut your camera.
Yeah. The internet connection seems to be. Let me cut off the camera and see if that helps. Okay. So the model, the behavior is still hydrostatic. So the problem and the hydrostatic approximation, that's a little bit surprising given that you get supersonic jets, but it's the geometric terms and the extra Coriolis terms that make the differences. I'm still not sure how important the differences are, but those geometric terms can be put into a conventional primitive equation model pretty easily. There are issues about what that does to energy conservation and so forth. But the reason those geometric terms, though small, are important is because they accumulate over a very, very long distance. of vertical motion. So the whole business of how important those are is tied in with this really troubling question of how the very deep circulation affects the upper atmosphere that you actually see. And there was the paper on GJ 1214b that one of Robin Wordsworth's students wrote, showing what an incredibly long time it takes to takes for the deep circulation to converge. And so I think that the issues of those non-traditional terms is really tied up with an even bigger issue of what we do about the bottom boundary condition for gassy atmospheres, mini Neptunes and things like that.
Yeah, Dennis, can I come in on that?
Yeah.
Yeah, so just to support that 100%, in the paper I was mostly focusing my talk on, we checked the hydrostatic across the atmospheric domain, and largely everything was in hydrostatic equilibrium apart from very small areas. And the reason is that, although you might expect supersonic flows, we sort of damp a lot of that stuff anyway. So largely that wasn't the issue. And as Ray said, yeah, just to confirm, it's the metric terms, and it's the fact that you essentially get cells flowing over a large regime. Now, of course, even if you only include the sort of radiatively forced bit and you've got an extended atmosphere, that can still get big enough. But then, as we were discussing a little bit yesterday in our breakout session, that's something I'm really intrigued by, about how you set off, I guess, indirect circulations in the deeper atmosphere. And a lot of us have, Robin has looked at that. I did some toy sort of experiment stuff in 2017 where I forced the deep atmosphere with a latitudinal temperature gradient that you might possibly expect from convection, which doesn't release heat isotropically. Typically, you do have a preferential heat release at the poles from interior dry convection. And things like that, and you do get this sort of coupling between the atmospheric flow that we see in the shallow atmosphere and that in the deep. And it is a really big problem, and it's something that's going to need much longer timescale simulations, or coupling between tools that are correct for the job, which is still a tricky job. One of the things we're looking to try and do at Exeter, which is going to be hard, is to couple a convective interior model, an anelastic sort of spherical harmonic model, something like an ASH or a MAGIC, and couple that almost like an ocean to an atmosphere model on the outside. Now, it's not as simple as an atmosphere and an ocean coupling, because you have motions that sort of come into the two different domains, and they occur over a larger scale height relative than the interactions you might expect on the ocean. But that's one way that we're trying to start to look at that problem a little bit more.
About that, do you think the time scale involved in the two model will be, does it make sense to really couple the two model, or you could just have lower boundary conditions coming from the interior model?
So yeah, great question. So I guess the real project aim is to start with a simplified boundary condition, where I think Adam Schoeman did this a few years ago in Zhejiang, where you have a sort of convective storm parameterization, and you start with that. And then we'll go into the next level, where we would take effectively an imprint from the outer boundary of a convective model and use it as a time-dependent boundary condition for the bottom of the atmosphere. And then ultimately trying to couple them on the time scale. I expect we'll have to do time scale splitting, just like between, say, the atmosphere and the ocean. And it's going to require something like a Dynamico, where you're not having a very efficient anelastic model being dragging a stone of a very inefficiently scaling atmosphere model. So the model of choice that I'll be trying to use is following very much what Dynamico has already achieved, and maybe things like Thor as well, is using the new Met Office model ELFRIC, which is designed to do convection permitting global simulations eventually. So it's designed to scale very well, and coupling that to this anelastic and trying to scale both codes very, very efficiently, and then but still having some sort of timescale splitting between the two.
Okay. Thanks, Nathan. There's also a comment from Ray in the chat regarding the timescales of coupling Yeah, it's quite interesting. So perhaps if we look, if we also focus on another domain of within the model domain, namely the upper levels, there was also some discussion about how to implement the sponge layers correctly, especially for a very high atmosphere, and especially for example, for tidally locked planets where you have a big jump between the day side and the night side. So I was wondering if anyone has any comments on that.
Yeah, this is Ray again. Let me turn off my video so that I don't know what's going on with my connection. But sponge layers are a real headache because to keep them, you can't actually put in a thin sponge layer. If you've got gravity waves going up there, if you put in a thin sponge layer that's very viscous, it's just like having a rope stuck in molasses. It'll be a reflecting boundary condition anyway. You have to put such a deep sponge layer in that it can be half your domain. So that and there's no for nonlinear waves and even for linear dispersive waves, there isn't any really good precise boundary condition you can use to just let waves go out of the domain. So it is a major problem that we'll all have to cope with. But it's a particular problem when you get to say very optically thick atmospheres. And so we've been trying to do 3D simulations of water-rich atmospheres, and water vapor is so incredibly optically thick, most of your radiation comes from the top 100 millibars or even 10 millibars of the atmosphere. And so you need a lot of resolution up there. And then if you're worried about what's going on with convection and sponge layers, you need even more resolution above that layer that's actually doing your radiative transfer to keep the dynamics right. And so it is a big challenge. Aside from throwing huge amounts of computer time at it, I don't know how to deal with it. It's been one of the things that's been really holding up our ability to do steam atmospheres accurately.
Okay, Russell, if you unmute yourself and speak.
Yeah, well, I was actually curious. In my talk, I kind of discussed it as like a necessary evil in some cases. But I was actually curious about, for example, like thermospheric models, what they do, and if coupling with a thermospheric hydrodynamic perhaps model of some sort would get us around the issue of having to use sponge layers. And I don't know if Eric Wolf is on, but maybe he knows a bit more about the Wacom and the NCAR Wacom model, and if it would help with this issue at all.
Maybe
Hi,
I
Russell,
can say.
Oh yeah.
I was just going to say that I'll be honest, perhaps if Howard Chen is around, he might be able to weigh in more about Wacom than I mean, Wacom goes up to 140 and 150, or 140 and then 500 kilometers for its model top, but it's highly tuned for the Earth. It's sort of a bear to work with, and it's also still a hydrostatic model, unless they've made some very recent changes to it. So, I'd have to look a lot more into it to give a satisfactory answer that you're looking for at the moment, Russell. I apologize.
Maybe I can say a word about our experience with planetary model. We go up to, you really cannot use the, this will be discussed tomorrow, I think, but you cannot really go above the exobase 10 to the minus 8 Pascal, typically, because above that, it's an exosphere, you have no more collision. But below that, of course, when you go very high, you have a viscosity that really dominates. So it's the mean free path of the molecules and the atom that dominates, so that the wind are really damped and you don't really need a sponge layer anymore. Otherwise, my experience is that except for the very special, not special, but strong case that Ray has highlighted, usually, of course, you are sensitive to the results you get in where you have the boundary, the sponge layer, but usually the sponge layer does not really affect too much what is going on below, except if your sponge layer is too low. So I think you're right, Russell. If you go high enough, even if you're wrong, even if you're wherever your sponge layer is, you know that your physics is not good. You are, I don't know, you are assuming not LTE and it's non-LTE, and you're forgetting something. It's okay. And usually, if you play with the parameter of the sponge layer, it's okay. You below that, you're not too affected because the mass difference is such that, except if you have a very strong descent of air at a given location, particularly above the pole, otherwise the atmosphere is not sensitive to what is going on several scale high above.
Thanks, Francois. That's encouraging.
This is Dan Marsh. Can I chime in on Wacom?
Oh yeah. Go.
Yeah. So the as we just mentioned, molecular viscosity damps the resolved waves in the model if you have a top high enough. But one of the questions we had to deal with is how you dissipate parameterized waves, the gravity waves in the model. And so that's kind of one of the reasons why Wacom has its lid at 140 kilometers, is because if you have a lower lid, then you have to deal with dissipating the gravity waves and these waves. So you need a sponge layer. So if you put your lid at 80 kilometers, you need a sponge layer. So, and how you choose to dissipate the parameterized waves really determines the whole circulation. There's a lot of tuning involved. When you don't have any observations to tune to, that can be quite difficult.
But if the wave are parameterized, why don't you just put in your parameterization that they just go up, saturate, deposit the momentum, and that's it?
Michael, do you have a comment?
Yeah, I was just going to ask Francois, because I think your Mars model goes up into the thermosphere, doesn't it, Francois? So
yeah, that's what I said. I know we have the Venus model doing that and Pluto.
Yeah.
And to be honest, we might be a little wrong by many aspects. We have some data to compare with, and it's quite promising, but it's not as if we had, because there is a lot of assumption we make. To be, for everyone here is familiar with GCM, and there is nothing magic in thermosphere, because to first order dynamical core are still valid. So what you add is everything that corresponds to the fact that you have a very long mean free path of the molecule. So you have molecular viscosity, molecular diffusion, and molecular conduction. And then you have extreme UV absorption. You have non-LTE processes. And if you have an ionosphere, it can be a little exotic to have a Joule heating and stuff like that. Otherwise, it's the same. But so it's not that a problem to extend your GCM into the thermosphere. It's just you add parameterization. Except that we might be a little wrong with regard to assuming a thin layer approximation, assuming also the fact that you usually, as discussed before, you assume that the molecular mass has no horizontal gradient. That must probably be wrong in there, but it's an error, but it's another error. So we have a model, it gives results, it compare well with all the data we have. The good thing is that we have a lot of data in the thermosphere because you can fly in, you can measure things with UV spectrometer and stuff like that. But it's not as if you had a perfect data set. So that's all I can say. But there is nothing magic. In other words, it used to be, people used to think that you really need to have a thermospheric model coupled to an atmospheric model. I don't think it's that necessary. And nowadays, a lot of people go up with the same dynamical core.
I agree. Although the UM seems to be having some issues with extending theirs with the stability of their dicore. But I don't know whether that has to do with that it's a non-hydrostatic dicore, running into problems that we will in Wacom run into when we switch over to a non-hydrostatic core. Maybe
that's another stability problem is another story. You have to dissipate a lot. It's true. It's true.
I think Nathan Main would like to comment on that.
Well, it was something earlier actually, but I can comment on that as well. And I think it was Dan who said it. You're exactly right. So putting it up up higher in the UM is the code is not very diffusive. It doesn't damp numerically very much. So that's why it's a stability issue more than anything else. It was just to sort of try and slightly can make the comparison to hot Jupiters. When you have a terrestrial planet, say like a Mars or an Earth even, then sponge layers, you can make them very thin, etc. But what we've got in a hot Jupiter is very often extremely large day to night temperature contrast, very, very large. And what you have is, it depends on which model you use, of course, but in the UM and Thor, we have a height-based grid. So if you set your top boundary a particular altitude because you want to capture a particular pressure, you have to go much lower pressure on the night side. So actually a lot of the sponge layer that we use, it starts at about 3/4 up of the vertical domain and then sort of ramps up very rapidly. But actually a lot of it is for transient initial conditions. So we've done experiments where you can gradually remove the sponge layer, etc. But I mean, you definitely need one, but a lot of it is just that you start off and you're shifting a lot of hot stuff from the day side over onto a very cold column of gas that goes down to very low pressures. So any sort of waves there can break much more easily. And I think that's the problem that Russell and I both have with a height-based grid, is that we have this extra chunk of atmosphere that you're not modeling with a pressure-based grid for a hot Jupiter. And that extra chunk of atmosphere is very cold and very low pressure. And that, I mean, it's not quite, it's not going to be in the exabase or anything, but it might be pushing into a regime where our physical assumptions need to alter the way we treat things. So it definitely is, in that respect, a stability mechanism for largely just that region of the atmosphere. I hope that makes sense.
Yeah. Okay. Thanks, Nathan. Let's move on to the next session, and we can discuss the upper atmosphere tomorrow, where there's another session on it. So does anyone have particular questions to Aomawa or Anthony or Stephanie? I know that for Aomawa, there are a few questions from Thomas and Martin. Do you guys want to ask them again now?
Yeah, I would love to respond to them in this forum, so that, because I think other people would be interested in the answers. I'm happy to read them aloud, or if each person wants to repeat them.
We can, thanks. Yeah, I guess we can just start with Thomas, and he can just repeat his question.
Okay. So my question was about the hydrolytes that you mentioned during your talk. So just kind of salt. Mm-hmm. And so I was wondering, if we know the frequency of hydrolytes on solar system, icy moon, and if yes, then can we guess if they will have the same amount or percentage of chance to find that kind of hydrolytes for icy exoplanets as well?
Yes. So there has been an infrared detection of hydrohalite on the dwarf planet Ceres, and there have been lab tests done under the conditions of Europa, and they have showed that NaCl does form hydrohalite within like 80 Kelvin to 233 Kelvin, and that UV irradiation provides this incredible amount of sort of desiccation, and but that hydrohalite can form within under Europa's conditions. So to my knowledge, there's not been a detection of hydrohalite on Europa, but we have seen it, within the solar system, particularly on Ceres, and within some of the craters on Ceres. So that does lead me to believe that it is plausible to expect to see it if those conditions, if those temperatures get low enough on icy exoplanets and moons.
Interesting. So it's something that we need also to consider then when we try to use specific albedo for ice for exoplanet simulation, right?
Yeah, so the way that we parameterized hydrohalite in the GCM was, within the ice thermal code, you can go in we were using CAM and sea ice or SICE, and that set specifies a 2-band albedo for below freezing, but you can actually go into the ice thermal code. Oh, my daughter's attempting to disrobe me, so I will put my video on. So that when temperatures get below freezing, but not yet at minus 23 C, we specified a 2-band albedo for bare sea ice with precipitated hydrohalite in it. And so we had those albedo spectra and just put that in so that the ice thermal code would kind of interrupt the default setting. And then once temperatures got to, I think we did actually not minus 23 C, but just a comfortable buffer. We set it at about minus 40 C, just because there is that gray area where you might be starting to form the crust, but not fully forming it. So we wanted to give ourselves some wiggle room. And so at minus 40 C, or I think it was maybe minus 33 C, so we had like a 10 degree buffer there. Then we specified the 2-band albedos for a fully formed hydrohalite crust. And so then whenever those temperatures were encountered in the model, it would insert those albedos in. And so that's something that was relatively straightforward to do just by getting into the ice thermal code in the GCM.
Okay, and the change in albedo is actually quite strong, right? If I recall correctly from the talk.
It is, especially, it differs strongly from water ice at those infrared wavelengths. That's where you get the largest differences. And there was a question, or one of Martin's questions that it might make sense to address here, which was just how can this form if you've got oceans freezing? I think he was curious about the actual mechanism for hydrohalite to form. And I wanted to clarify that. So, you can imagine as ocean is freezing, sea ice would trap small inclusions of liquid brine within itself, within the sea ice. And then as temperatures continue to get cold enough, this has been postulated to have happened on snowball Earth. So as temperatures get cold enough for the salts dissolved in the brine to precipitate, you'd have these hydrohalite crystals once they precipitate. And both hydrohalite crystals and water ice crystals, for that matter, they would then occupy the full volume of the brine inclusion. And that's the point where you start to have this enhanced scattering of incoming light.
Okay. Yeah, interesting. Thank you.
Thanks. Ray, do you have a comment?
Yeah, first, I mean, a comment on the hydrohalite and the sea ice is thick ice like shelf ice, like as we showed in Snowball Earth. And so there's the question with regard to hydrohalite, there's the question of whether the surface is being formed by meteoric ice, which basically from snowfall that gets advected in from higher latitudes, or whether it's formed by frozen seawater, which gets up to the top. And especially in 3D, there are a lot of unresolved issues with how the ice circulation connects that are an interesting frontier issue in terms of where you would actually form the hydrohalite. But my question was on the other side of hydrohalite, the low albedo side. And I was wondering if you have any thoughts about dust, because in our snowball work with Dorian especially, we really found that a little bit of dust darkens the ice surface a great deal. But there are real questions about what happens when that dusty ice starts to melt. Does it self-clean and drain away, or does it actually, just melt, deglaciate?
Yeah.
I think that's another sort of frontier area in surface processes.
Absolutely, and that work, some kind of a study would follow nicely from something that one of my students is already doing. He's looking at the effect of cryoconite holes on these kind of glaciation, deglaciation thresholds. These cryoconite holes, which are little holes made by dust and soil within ice or snow. and how those would depress the overall albedo that might be parameterized in a GCM. This idea of sublimation is super important because, as you point out, if you've got, we find in our hydrohalite work that this parameterization, if not present in a GCM, can provide inaccurate results. Like, it's important to include it, and it's relevant even in the habitable zone for synchronously rotating planets, even more so. But of course, as the installation gets lower and lower, it becomes even more relevant, where you've got areas of net evaporation present. If you've got snow that falls on top of the hydrohalite, the albedo effect of hydrohalite is rendered completely inert. So snow on top of it totally takes that effect away. But if you've got the net sublimation or regions of net evaporation, then it's quite relevant.
All right, thank you, Amar. Martin, you also had some questions for our, do you want to ask them now?
Actually, I have a question for the ocean modelers in general. So Anthony and Stephanie and people from Rocky 3D, I would like to know if you have thought about possible strategies to convert your ocean models to non-water, I will say, ocean models like methane ocean, liquid CO2 ocean, magma ocean. What kind of developments, numerical developments or development in general would that require to move your ocean models toward this direction? I would be curious to have your opinion on that.
Hey, Martha. We haven't, we just started modifying the ocean model and comparing it to Rocky 3D for deep oceans. Switching to liquid hydrocarbons, like you can find at the surface of Titan, would require quite a bit of rework of the ocean and the sea ice as I guess the ice form of methane and ethane might form differently than for water. So to answer quickly, no, we haven't started thinking yet about switching to different form of liquid, but that's probably something we need to do in the future.
Francois, do you have a comment? Francois?
Sorry, I use my space bar, but it doesn't work. Yeah, I had a question for Stephanie. And my question is about science to conclude the session. It's really scientific. I wanted to know what is the current, what are the current thoughts about the saltiness of a global ocean on early Earth, and whatever speculation there is about how salty will be a global ocean on an ocean planet. What are the current thoughts?
Well, that is a great question. In regard to early Earth, there are extremely limited proxy constraints on the evolution of our ocean salinity. And we don't even have predictive models really for what it should be. So many years ago, Dick Holland noted that if you just take all of the evaporites on the continents and you put them back into the ocean, well, then Archean salinity should have been higher than today, maybe 50 PSU. Paul Nauth noted that if you stir back in deep basinal brines and you just put all the salt we know about into the open ocean, maybe it was as high as 70 PSU. The one data point based on the geologic record actually points to potentially lower than present day salinity. And so I would say that this is a wide open question. We have no idea. And then when we go to exoplanets, it's really, I think the biggest uncertainty that we face is just how much water they're starting with to begin with. Because that's even an easier way to change the salinity, is just change the volume of the ocean for a given planet size. So I think that kind of the full range from relatively fresh to potentially near saturated oceans are probably possible elsewhere.
Okay.
I think Ray has another question. Ray, please.
Yeah. Some remarks about the non-water oceans. Of course, if you take an ocean of almost anything other than water, one of the most important things that's different about ice is that CO2 ice sinks in liquid CO2. And similarly, pure methane ice sinks in liquid methane. Although you could actually have mixed phase ices like ethane, methane oceans, things like that. But so the kind of it would be, I don't think it's ever been really looked at in a GCM, but the sort of situation where you get a glacier on the bottom of your ocean because your ice sinks to the bottom. It is a really fascinating regime, which would be relevant to certainly to a CO2 ocean. But the magma oceanography is that's quite important for lava planets, and nobody's really touched that either. Basaltic magma has a viscosity not too different from water, and much denser, which changes things. You're not going to get much wind-driven circulation, but the mixing within a magma ocean would affect the exchange with the atmosphere and things like that. And so these are things, we're just using 1D models of magma oceans right now to look at magma ocean evolution, but magma oceanography, I think, is going to be a very important growth area, not for habitable planets, but for planets that go through a magma ocean stage. But getting back to just ordinary water, salt oceans, something that concerns me about exooceanography is that the mixing processes like Gent-McWilliams and also the diapycnal mixing from vertical mixing, we know they're extremely important to the global ocean circulation, but the ocean models are very heavily tuned to the current Earth-like conditions. And I really don't know how you, aside from maybe parameter sensitivity studies, how you actually face the issue of what Gent-McWilliams parameters, what vertical mixing you should put into an exo-ocean, especially since a lot of the vertical mixing is due to tides and bathymetry. So leaves me being a little bit uncertain about the exo-ocean studies so far, but I don't know what the way out of that is.
You're totally right. Right. A lot of the values we're using are based on Earth values for now, and I guess we're going. It's a brand new field, so we're going to have to rework all of our diapycnal diffusivity and convection. There's a lot of work being done on parameterizing convection plume, like the heat rising from the seafloor, whether it's from radiogenic decay or tidal heating, and the way it interacts with the whole ocean depth, and potentially, if it's a subsurface ocean, with the boundary layer at the top. So it's there's still a lot of work to be done.
Thanks, Anthony. Sean, do you have a comment or question?
Yeah, I have a follow-up question for that discussion Stephanie was just having about ocean salinity. If we were trying to model either a specific exoplanet or a generic one, what would your recommendation then be for salinity? Is it something where, because it's unknown, we should just parameterize it and simulate everything as you said, from relatively fresh to saturated? Or, I mean, what would your advice be if when we are running these simulations, given that this could have an impact on the
Yeah, I think that's a reasonable starting strategy. Our default currently is just use a present-day Earth salinity, either explicitly or implicitly if we're using a slab ocean. And I think that a reasonable path forward would be to consider a relatively low salinity scenario and a relatively high salinity scenario to try to bracket the range of possibilities. Because in some circumstances, it'll matter a lot. Like in my Archean Earth ones, it's a pretty cold planet to begin with, and it has a big impact. I think the impacts will be less important on relatively warm planets. And on tidally locked planets, there's potential for muted impact as well. So I think sometimes it'll be really essential for understanding habitability, and sometimes you might be able to get away with without considering it fully.
Thank you. Jun, do you have a question?
Yeah, I agree with Ray. I just a comment that I agree with Ray that ocean mixing is especially for deep ocean mixing is unknown for exoplanets. But a good thing is that when we study Earth, we know that the deeper mixing, most of the ocean heat transport is from the upper ocean. The Meridiana ocean heat transport for the deep ocean is very small. So if we focus on the ocean heat transport, such as from the tropical to polar regions, or from the day side to night side on tidal planets, most of the heat transport should be from the wind-driven ocean circulation. The heat transport of deep ocean circulation is small. This is due to that the temperature difference of the deep ocean is very small. On Earth, we well know that. So I think this is good news, although we don't know the mixing.
Nathan?
I have to go, but as someone that's considering adopting a model ocean into our setup, I think the summary could be, and correct me if I'm wrong, that I definitely need an ocean, but we just don't have any idea how to set it up. Is that fair? Okay, good. All right, so keep working and let me know when we have an answer.
Perfect.